So in this video, we're going to kind of do another Calculus 1 refresher, but this time for integrals. So you still need all of your Calc 1 skills with basic integration. You need power rule, you need U substitution. So I'm going to briefly kind of try to refresh your memory on all of that by example. I tend to teach by lots of examples. So when you take a look at number 1, you can integrate term by term, just like you can take the derivative term by term. You can look at each term separately. So because with integration, we're kind of going in the opposite direction, what I really want you to think about integration is you've got a derivative presented at you, and you're being asked, hey, find the original function that it came from. So you're kind of going in this, like I said, I always view it as like an opposite direction. You have a derivative in front of you, and you want the function that when you take the derivative, you get that. All right, so 2x minus 5 is the derivative of something. What is it the derivative of? So what we're going to do is use that power rule. So I am going to just leave the coefficient there. The 2 is just kind of hanging out. And the power rule is, this is really x to the first. So I'm going to add 1 to the exponent and divide by 2. The antiderivative of negative 5 is negative 5x, and then I'm just going to add a plus c. So I can certainly cancel those 2's there, that coefficient of the 2 that was there, and end up with this as the integral of 2x minus 5, or you can say the antiderivative of 2x minus 5. And you can always check your work with this stuff. If you feel like, I don't know if that's right, let me just see. You can always use this as a little trick for yourself. You can always take the derivative of that final answer from your integral. Don't forget about this. Take the derivative of that, and then you end up with the original statement. And so you can realize here, oh, I made a little mistake there. That should be a minus sign. See? There we go. And you pick up little mistakes that you made. So you can put a check mark next to that. So it's kind of nice that you can check your work. With a derivative, you're just kind of crossing your fingers, you hope for the best. When it comes to number 2, this is a problem because there is no product rule for integration. So I need to kind of scream that as loud as I can. There is no product rule for integration. I have ways of handling it, and also let me add here, there's also no quotient rule. Again, I need to scream this as much as possible because integrals don't have those two things. Now with number 2, I do have strategies to handle it, and we're gonna take this and go further in this class. There's a lot more strategies that we can learn, but this one is really just an algebraic maneuver. There's no reason you have to leave these two guys, this monomial multiplying the binomial. Let's just multiply it out. I mean, that's the simplest technique ever. I can get around this problem pretty easily. Okay, so at this point now I pretty much transformed it into what number 1 kind of looked like. You can handle it term by term. So I'm going to do the same thing. The 6 is just a coefficient. I'm going to add 1 to the exponent, divide by my new exponent. Same thing with the next term. So there is my integral. I'm just going to clean it up a little bit. And there is my final answer. Okay. So again, all of this stuff you've kind of been around the block a few times, especially if you're just coming off of a Calc 1 class. This should all be really manageable. When I take a look at the next 2, this one is getting a little bit trickier, right? Because now you have the 2x minus 5 inside the sine function. There is no algebraic way of handling this. You cannot distribute the sine function like I distributed the 3x squared in the last example. It does not work like that. Pre-calculus, I'm sure, drove that home for you. And, there's some things I know. I know that, the integral of sine is negative cosine. But there's something else inside that sine function that I have to address. So this is where you have to use one of those more fancier skills that you learned in Calc 1, and this would be a U substitution problem. So U substitution, just to refresh your memory, is it was based off of the chain rule for differentiation. Again, there's no chain rule in integrals, but this process kind of came out of the chain rule for differentiation, where I'm going to basically say, hey, I am going to make something up. I am going to let U equal 2x minus 5. A really good first choice of U is something inside something composite. So that would be this 2x minus 5 sitting inside the sine. Now, you had a lot of different instructors in your life, especially for Calc 1. I have a tendency to just follow through this, meaning I take the derivative of both sides. I take the derivative of U, I get du. I take the derivative of 2x minus 5, I get 2 dx. And then I solve this thing for dx. I just algebraically solve that. And so here's what's happening. I am going to rewrite my integral that I was given at the start. I kind of left the sign alone. I'm not really doing anything with that. But I'm replacing all of that stuff inside with U. And the reason I kind of solved this thing for dx equals is because you got to get rid of that dx. You're switching everything to the U variable. That dx has to go, and legally the swap for dx is du over 2. So you've just transformed the integral into something friendlier that you can do. So I'm going to switch back to purple here. That over 2, I'm just going to pull that out as a 1/2 coefficient. And U substitution allows you to take something complicated and recreate it into something that you know how to do. The integral of sine is negative cosine. So let's go ahead and do that then. I'm going to have 1/2. My integral is negative cosine plus c. I certainly can't box my answer like this because, you are presented with an integral in terms of the x variable. Your answer should be in terms of the x variable. So the last step here is to just convert it over. I'm just going to take that negative and put it on that negative 1/2. And then, remember, u was 2x minus 5, so I just dropped that in. And again, if you were unsure about this, trig sometimes makes people a little bit uncomfortable, you could certainly take the derivative of that answer and end up with the original statement. And that would make you feel better about, hey, that has to be good. Okay. On the topic of trig over here with example 4, okay, there is no, there's no algebra that you can do necessarily on cosine squared. A U substitution is not your best guess here. What I want you to do is rethink what 1 over cosine squared is. You do have a trig identity that you could use on this. You know that 1 over cosine is secant. So if you have 1 over cosine squared, which essentially is what this is, you have 1 over cosine times 1 over cosine. Each one of those is secant. So I have secant times secant. Let me write that. And you have to think in terms, trig always bothers people, but you have to think in terms of what this means. Again, what you have is the derivative of something. If I go back to this image up here, hey, that's the derivative of something. What's the function that secant squared is the derivative of? And it turns out it's tangent. So no fancy techniques here, just really knowing trig really well and really knowing your derivative rules for trig as well as the flip side, the integration rules. Okay, all of this is Calc 1. All of this is necessary in this class. Okay, so now we have two next examples here. You see the 4x squared minus 7, just kind of playing around with it a little bit. On question number 5, again, there's no quotient rule for integrals, but I can deal with this. I can deal with this pretty quickly, actually, if I handle my good algebra skills. This is something where I don't want to bring U substitution in unless I exhaust all other options. And for this one, I'm going to bring that square root of x kind of up. So let's see. So I'm going to make that a 1/2 power, and maybe I'll write it like that. Like that. I'm just switching the square root for a 1/2 power. And then what I can do algebraically, this is like algebra 1 here, I'm going to bring that up with a negative exponent. I think we've discussed that before. And then I can handle this the same way that I did problem number 2. You've got a monomial times a binomial. There's no reason these have to be separated as a product. You know, I still have a problem, but it's a solvable problem. I'm going to multiply that x to the negative 1/2 through. And so again, what you've done is you're changing the expression of that statement, but you're not changing the value. You're just making it easier to work with for your integration side of things. So I'm now actually ready to use that power rule for integration. Remember, the 4 is just kind of a coefficient hanging out over there. I am going to add 1 to the exponent. That's 5/2, and then you divide by 5/2. I'm going to add 1 to the exponent, and I'm going to divide by that new exponent. And just to be clear here, normally I don't write it this way. It's kind of weird to have like you're dividing by a fraction. A lot of people don't like that. So let me write it. When you're dividing by 5/2, you're actually multiplying by 2/5. So a lot of times you'll see me jump to that step. So again, instead of dividing by 1/2, you're really multiplying by 2. You're multiplying by the reciprocal. And then I'll just clean it up. Now, it's up to you. You can leave these as rational exponents, as these fraction exponents. You can switch back to radical form if you like that, but this looks good. Okay. So maybe I'll rate it that way just to see what you prefer. That's equally awesome. Okay. All right. So when you take a look at number 6, this is one that is not as easy. Dare I use that word? It's not as simple as the denominator in question number 5. You just have a square root of x. It's one term down there. It's a monomial. You can bring that up and distribute. This is much more complicated of a denominator. That is a composite function down there. It is not, great. So I want you to view it as that. You have a lot more going on under that radical, and that to me is the tip off of you know what? Let's use that fancy method. Let's do a U substitution, and your best first choice of U is what's inside something composite. So that 4x squared minus 7 is a good candidate for knocking this down, making it simpler. It's a very complicated statement. So once I decide to use this U substitution technique, I have a tendency to just do what I consider the follow through, which is take the derivative. And the point of doing this is if I'm going to switch that whole denominator, that inside junk to be a U, I have to get rid of the dx. So I just legally solve to get the dx by itself. Okay, so I'm going to come back to this integral, and I'm going to say, look, I have the integral, I've got x over there, I've got the square root of u. So let me just throw that in there. I'm knocking that whole thing down and just saying u is that whole thing underneath. And then instead of this dx over here, I can't leave that hanging in there. I need to write its equivalent, which is du divided by 8x. Now with U substitution, as you probably remember from Calc 1, it only works if you're able to eliminate the x variable in its entirety. You can't have any x's left over when you use this strategy, and you can kind of see here, I have accomplished that goal. Those x's are gone. I do still have that 8 in the denominator, but I'm not really bothered by that because that's just a coefficient. Those things just kind of come along for the ride in calculus, and I don't have to worry. I think I'll switch that square root to a 1/2. And I'm now ready to kind of think about, well, what's the integral of 1 over u to the 1/2? Let's write what that is as a power, bring it up. You can handle this. You can add 1 to that negative 1/2 power, right? That's how you use the power rule, and divide by your new exponent. So I'm going to do that. Let's see, if I add 1 to negative 1/2, that's u to the 1/2. And dividing by 1/2 is the same thing as multiplying by 2. So see how I just did that in one step. And then, again, I should switch back to the x variable. So what I'm going to do is just like get those together. 1/8 times 2 is 1/4. And then instead of writing u, I'm going to write 4x squared minus 7 to the 1/2. So again, I think this is great. And I also think you could switch back to radical form if that makes more sense to you. Okay. So let's move on to the next two down here. And kind of just show some differences here. So something like number 7, I can't handle this the same way I handled, let's see, example number 2. I am not allowed to distribute that 3x under that radical. That's a power. It's almost like rules of exponents are stopping you. Let me show you what I mean, maybe. Like, PEMDAS. You have to handle like exponents before you multiply. So you're not allowed to get into that x minus 5 to the 1/2 power. However, this does sort of lend to the idea of like, well, it is a complicated integral. There is no product rule. What do I do about that? I can't algebra maneuver my way through this. But I do see something inside that radical. I see that x minus 5. This might be a good candidate for u substitution. So you just kind of try. A lot of times you don't know if the u substitution is going to work out or not. You just kind of go for it and see if it does. And by work, I mean, can you get rid of the x variable everywhere? So right when I start with u substitution, I do the follow through. I take the derivative of both sides because that gives me my swap out for the dx. So let's transform this integral. You've got 3x that I didn't touch. And then you've got this thing to the 1/2 power. And that thing to the 1/2 power is exactly what I let u equal. And in place of dx, I can simply write to u. That's legal. That I checked that out. I can do that here. So now, I'm not bothered by the coefficient of 3. That's just a number. Nobody cares. But the x there is really bothersome. So what I can try to do sometimes, because this substitution is pretty friendly, there's not a whole lot going on here, what I can do is take that substitution and kind of wiggle it around. Let's solve that for x. Let's just add 5 to the other side. I mean, this is a true statement. If we decided that u was x minus 5, then it would make sense that x would be u plus 5. I can use that to my advantage here. I'm going to do that. I'm going to make that swap. So here's my original integral, right? I'm not bothered by the 3. But instead of writing x, I'm going to write its equivalency, which is u plus 5. And then I still have that u substitution there of u to the 1/2 du. This is mission accomplished right here in terms of you have gotten rid of all of the x's. You have totally transformed this integral from the x variable to the u variable. I am not out of the woods yet because now I have to see well, can I actually integrate this? Again, there's no product rule for integrals, but I am allowed to distribute the 3 in, and I can distribute the u to the 1/2 in. So let's just throw those guys together. Remember, multiplication is commutative, so you can do them in any order that you want to. And now I can kind of throw these guys in. This is a maneuver that you can handle algebraically. I can distribute that 3 u to the 1/2 times u. Remember, that's where you add exponents. And I will also distribute it to that 5. Now you're at a moment where you can legally distribute and it's great. And this is definitely, you're right in that zone of power rule. I'm going to do that. I'm going to add 1 to the exponent, and dividing by 5/2 is the same thing as multiplying by 2/5. And let me not forget about that 3 that was hanging out over there. I'll do the same thing on the next one, right? So you've got I'm going to add 1 to the exponent there. That would be 3/2. I'm going to divide by 3/2, which is the same thing as multiplying by 2/3. And the 15 was already there. So now I'm just going to kind of consolidate and convert. It's not okay for you to box this answer because, your integral was in the x variable. Your answer should be in the x variable. So I'm going to clean up these fractions. That's 6/5. And then in place of u, I'm going to switch back. Remember, u was x minus 5. So just make that switch back. I'll do the same thing over here. That coefficient, that's 30 divided by 3. That's 10. And don't forget those constants of integration. These are all indefinite integrals, which is why I'm adding that plus c. There could have been some number in your function there, and so you're representing that. Okay. As I slide over to question number 8, well, this is the only definite integral in my example set here, and once again, very similar ideas here, right? Like, this is a definite integral. I'm going to ignore that for the minute. We'll handle it. But you have something outside this binomial raised to the power of 3, and you have the same algebra problem. You can't distribute that x squared in there. You absolutely cannot, because you have that power of 3. That PEMDAS rule, order of operations, is what's preventing you from doing that. So you can't do any algebra to solve this problem of, hey, I've got a product going on here. What you can do is the next best thing. This is the one strategy that you learned in Calc 1. And again, it's that U substitution. It's so important that you are good at U substitution, because even though in this class we are going to, even though in this class we're going to learn a lot more strategies, the most used strategy is still U substitution. So this is really important. And if this is bothering you, then you can look in section 4.5 of the textbook. Online, there's the ebook within WebAssign. So my best first choice of U is something inside something composite. So I keep saying the best first choice because sometimes you might get it wrong. There's no steadfast rule of what always is going to work. It's a strategy, so you just try to apply it. So once I decide what the U is that I'm going to try, then I do what I consider that follow through, and I take the derivative of both sides. And then I'm going to come at this and I'm going to integrate this. Now, I'm going to leave the limits of integration off for a second. I'm going to kind of switch this around. I'm just going to leave it off. And I'm going to make sure that I put that U in there. So you're toning it down. That x cubed minus 2 is now represented with u. And also over here, I'm going to replace what dx is. So if du is 3x squared times dx, that means dx is du divided by 3x squared. And you need to take a step back before you do anything else and say, did I successfully convert this integral from x's completely over to u? And the answer is yes, you did, because that x squared will cancel out. That's what you're kind of looking for. I'm not bothered by that 3 down there in the denominator. That's totally okay. I can just pull that out as a 1/3 coefficient. But you have satisfied and totally transformed this really complicated looking integrand into something very manageable. So I'm going to actually finish this out. I'm going to find the antiderivative, and then I'm going to switch back to x. Now I'm going to do something interesting here. I am not going to put a plus c. Okay. The reason is I have a definite integral. So let me get my integrand back into the x variable. And now let me use that fundamental theorem of calculus, FTC. where we actually come up with a number here. If you have a definite integral, your final answer is a number. Could be positive, could be negative, could be 0. And that's how I handle these limits of integration. I'm going to take that antiderivative. I'm going to plug 1 in for x. And then I subtract. Now I'm going to plug the lower limit, the 0, in for x. So it's always you plug the upper limit of integration in and then the lower limit of integration. I got to put that power back in there. Okay. And then I'm just going to evaluate it. So again, no calculator, but no problem. 1 cubed is 1. 1 minus 2 is negative 1. 0 cubed is 0. So that's negative 2 to the 4th. So what I have here is, well, that will be positive 1. 1/12. And what is that? That's positive 16. 1/12 minus 16/12. That's negative 15/12, which I think is a pretty good looking answer, but maybe we should reduce. I'll divide everybody by 4. Negative, or by 3, I'm going to do negative 5/4. That's my reduction, my reduced fraction for negative 15/12. Okay, so, you know, you can go back into chapter 4 if you need a little brush up on these skills, and it might just take, you know, 20 minutes to look over some things. Here are some problems that you might want to do from chapter 4, but you can just look at section 4.4 and 4.5 because that's what we focused on mostly in this refresher of integration. I did a refresher for derivatives, so I wanted to do a refresher for the integrals before we got into some new things that you may not have seen in Calc 1.